Thanks for that introduction. My name is Cónal Murphy. I'll be talking about the theory of high radiative recombination rate and broken gap in the arsenic gallium tied superlattices for mid-IR applications. So I'll present our motivation, some of the theory associated with this work, some of our results, and we'll finish with a brief summary and conclusions. So there's a strong interest in developing mid-IR LEDs and laser sources for gas sensing applications like environmental monitoring, medical diagnostics, and industrial process control. Typically, efficient and reliable devices have been difficult to produce at this wavelength. This is because of some things like non-radiative processes like Auger recombination, which is strong in narrow gap materials encompassing mid-IR devices. So we can see here that our Auger coefficient C depends on the gap. And some structures that have been tried, such as type 1 quantum wells, shown promise in the 2 to 3 micron spectral range. However, performance typically degrades with increasing wavelength and high threshold currents and temperature sensitivity that's associated with non-radiative processes. Interband cascade lasers in the 3 to 4 micron wavelength range have shown promise but require sophisticated growth. And above wavelengths 4 microns, quantum cascade lasers have been widely used, but are complicated structures and suffer from degradation for shorter wavelengths. So in this talk, we will establish a theoretical framework to efficiently compute optoelectronic properties of these superlattices and explain the high radiative recombination rate observed in these type 2 superlattices. So in our model, we employ a plane wave expansion method with an 8-band K.P Hamiltonian, where we write envelope functions as a Fourier series with discrete wave vectors GM along the growth direction. Typical quantum well calculations are for ignore any miniband dispersion. And we include this miniband dispersion by taking our parameter GM to GM plus KZ, where KZ describes the periodicity along the growth direction, encapsulating that miniband dispersion. We assume an infinite periodic superlattice along Z and compute eigenstates as a function of in-plane wave vector, like typical quantum well calculations, as well as KZ. We can see how our integral changes our computation of spontaneous emission density of states, where we're considering the impact of the miniband dispersion. And all these calculations are highly efficient, as our plane wave basis set typically requires smaller matrix sizes than that of real space finite difference methods, and the calculation is also parallelizable over wave vectors by running for a different wave vector on a different core. So here we compare our results for an analytical chronic penny model to a 1-band plane wave expansion method. So on the left of the figure, we can see the associated potential. So the chronic penny model is a solution to Schrodinger's equation for a 1D superlattice, and it gives a transcendental equation whose solutions can be found using a root finding method. And by including the miniband dispersion in our 1-band plane wave expansion, we can see that we can recreate the analytical chronic penny solution. So this verifies that the plane wave expansion method can be used to efficiently compute the miniband dispersion using a calculational supercell of just one single period. So moving to some of our results, we simulated an indium arsenic gallium antimonide superlattice with supercell period of 4.6 nanometers, and it consists of equal layers of 2.3 nanometers. So in this plot, we show type 3 band offsets. So we can see that the valence band edge is higher in energy in the gallium antimonide layers than the bottom of the conduction band edge in the indium arsenide layers. And we can see moving left to right, repeating periods for illustrative purposes. So the dashed lines demonstrate the E1H1 ground state energies, which also correspond to the 0 probability density. And we can see that the hole probability density goes to 0 in the indium arsenide layers, while the electron probability density does not do the same in the gallium antimonide layers. So we see strongly confined holes due to large gallium antimonide hole effective mass and somewhat delocalized electrons due to the narrow layer thickness and the small indium arsenide electron effective mass, noting that quantum confinement opens a band gap. So based on these results, we expect good electron-hole wave function overlap compared to conventional type 2 structures, and this will give large interband optical matrix elements and radiative recombination. So here in this plot, we see, moving left to right, the mini-band dispersion, the in-plane dispersion, and the associated density of states. This is presented for 4 Kelvin with a carrier density of 10 to the 17 carriers per cubic centimeter. So the line color corresponds to a Fermi distribution occupation weighting. So as the line gets darker, we see higher occupancy. So at 4 Kelvin, we see step-like Fermi distribution, which gives step-like band occupation. And if we look at the left-hand part of the figure, we can see that the E1 miniband possesses a strong dispersion. So this means that electrons will only occupy states in a limited range of kz values. And in contrast to this, the H1 miniband is almost dispersionless, meaning we'll see holes occupied out to large values of kz. So here now we see the similar results except for 300 Kelvin. So at 300 Kelvin, we see smoother band filling due to the softer tails in the Fermi distribution, which extend beyond the quasi-Fermi levels. And as a result, we see electrons occupying states across a greater range of kz than that of a low temperature. And this is kind of all important to note because optical transitions require that delta K is equal to 0. So these calculations indicate that miniband formation will serve to suppress radiative recombination. So presented here are the calculated TE and TM polarized E1H1 optical matrix elements. So the in-plane optical matrix elements obey conventional selection rules, where TE polarized is allowed at K parallel equal to 0 and TM polarized is forbidden. So at K parallel equal to 0, we can see that the transition strength is approximately 40% that of the bulk in de-Marsanite Kane parameter. And this is very high, which we attribute to the electron delocalization. Then as we move away from K parallel equal to 0, we can see the effects of band mixing as TM polarized becomes non-zero. And then along KZ, we can see that the TE polarized optical matrix element decreases as a result of changing phase of the E1H1 wave functions, eventually becoming 0 at KZ equals pi over L. And we do expect spontaneous emission to be dominated by TE polarized radiative recombination. So here now we show the spontaneous emission spectra at 2 different temperatures, 4 and 300 Kelvin. The grey dashed results are for a single KZ equals 0 calculation, and the solid black results are for a full superlattice calculation. So following on from our analysis of band filling, we observe the impact of miniband formation in reducing the peak spontaneous emission rate. And as expected, the reduction is less at room temperature due to the mismatch in band filling. And we note as well that the temperature-dependent spontaneous emission peak energy is in good agreement with experimental measurements. So now, if we take our spontaneous emission results, integrating over wave vector, we'll obtain our radiative current density. And then by applying the Boltzmann approximation, we can then extract the radiative recombination coefficient B. So we can see that B displays one characteristic 1 over T dependence, and that at low temperature, we see strongly suppressed B values in comparison with the KZ equals 0 calculations, and that as we approach room temperature, B approaches the values from the calculations, ignoring any miniband dispersion. And we see these results following on from the band occupancy mismatching previously mentioned. And then at the table, at the bottom of the slide, we compare results to metamorphic type 1 structures and dilute bismuth type 1 quantum wells. These results are from similar methods. So we can see that B in these indi-marsanite gallium antimonide superlattices compares favorably with these type 1 quantum wells, and that these superlattices have quite strong electron-hole wave function overlap despite the type 2 like carrier confinement. Our calculations attribute this to the electron delocalization, providing relatively high spatial wave function overlap. And then if we move here, so moving on from analysis at fixed thickness to look at things as a function of the layer thickness, we can see here extracting our emission wavelength from our spontaneous emission spectra for various thicknesses. We can see that the emission wavelength is quite tunable via the thickness. And we can see that the superlattice calculation wavelengths are blue shifted compared to the KZ equals 0 calculations, again kind of highlighting the importance of the full superlattice calculations for device design. And then if we look at the other figure, we can see our radiative recombination coefficient as a function of thickness. And we can see that with reducing radiative recombination, we can see reducing radiative recombination for increasing thickness. And semi-analytical calculations attribute this to the reducing optical matrix elements. So that means that at small t, we see greater penetration of the E1 state into the gallium antimonide layers, which will increase the wave function overlap. And that as you increase thickness, you'll get reduced penetration of this state into these layers, and that'll reduce the electron-hole wave function overlap. So this increasing T leads to reducing optical matrix elements, which in turn will lead to reducing radiative recombination coefficient values. So to sum up, We've presented a numerically efficient method to compute superlattice optoelectronic properties beyond the capabilities of commercial codes. And this technique can be applied to arbitrary 3-5 superlattices. We've seen the impact of miniband formation on radiative recombination, and that a mismatch in the number of holes and electrons available to recombine will lead to a reduction in the radiative recombination rate, and we will see a larger mismatch for lower temperatures. However, we still do see high B values as a result of this good electron-hole wave function overlap, and that it's important to note that at larger temperature, we will see a better match in the conduction and valence band occupation. So in terms of outlook, just highlight that by varying the layer thickness, we can tune various parameters as we've seen. And by introducing strain, it would be possible to engineer hole effective masses, which will lead to control over this band filling mismatch. For a narrow gap system, we expect strong Auger recombination, as mentioned in the introduction, which must be investigated for more rigorous device design. And all this is with the intention of optimizing the internal quantum efficiency. And we also note that our high B values imply high optical absorption, which indicates promise for photodetector applications. So I'd just like to thank funding bodies, collaborators, and thank you for your attention.